introduce company. So today we are going to look, as you can see the title, Novel Ensemble-Based Techniques for the Preemptive Diagnosis of Rheumatoid Arthritis disease in the Eastern Province of Saudi Arabia using clinical data. This is in following our regular selection of selected application of machine learning to some areas of endeavor. So recently we got a comment from one of our participants asking for kind of a regression problem. Inshallah, after completing this particular selected paper, we're going to look into how we can also apply it to regression problem. For example, we're going to look into soil contamination. How can we use it to estimate or to model soil contamination and the treatment? So there are so demonstrating there are so many areas that we can just imagine and think of in our various areas of endeavor that we can apply machine learning to. So for this current one is based on rheumatoid arthritis. So some of us might be aware of this. Surely affect the joints, especially in the leg. So at the knee position. And the idea of this work came in when one of the top management lead in during one of our showcases for our previous project demanded that rheumatoid arthritis will be very, very important for us to look into, because often it's very difficult to diagnose by practitioners. So if there's any way machine learning can really come in. So we look into that. We were able to get a couple of data sets. Specifically, this is targeted as predicting it using clinical data. Just maybe a little bit of question like the age and also the blood count, complete blood count test. So these are basic tests that anyone can do in any laboratory. But surprisingly, this, as simple as it is, without X-ray, without whatever you think of, we're able to achieve considerable kind of amount of performance improvement. This paper was recently published in what I think what is termed the computational and mathematical methods in medicine. So it's a Q1 ranked journal, I think, with the impact factor stated. So it's listed by our university as one of the Q1 journal list. So the aim and objective of the work was actually to preemptively diagnose rheumatoid arthritis. That is, the idea is that if people can do, when people go for regular medical checkup or blood count test, can we really use this to really determine if this person might likely suffer from this disease before it actually starts? Now, so like I was saying, so the idea of preemptive diagnosis is to diagnose, to get to know if this particular disease is present at the very earliest stage, even before the symptom starts. So using very simple clinical data set. So we also want to look into the employment of machine learning techniques, and then the combination. We want to employ machine learning techniques and combine them via voting ensemble. To see what can we have of ensemble. So also we try to utilize feature selection to reduce the number of features, even though there's still need to do more in terms of the feature selection. Now, the utilized classifiers include support vector machine, logistic regression, adaptive boosting, and finally the newly proposed voting ensemble. So support vector machine modeling was carried out, logistic regression and adaptive boosting. Following these three, then a voting ensemble came up where you have SVM, logistic regression and adaptive boosting as a kind of combination, as a committee of classifiers that we can now try to combine their decisions together to achieve hopefully better results. So on the description of data sets, you said the data set utilized to perform this experiment was driven by integrating two clinical rheumatoid data set obtained from Kemfad University Hospital. So the first data set contained 196 instances, while the second comprises of what? 262. So we merge the two together, we are able to come up with 446 instances. So with 31 attributes, because when you try to combine, this fall under pre-processing and data preparation. When you try to combine two data sets together, you have to make sure the features are unique. So we have to select features that are present here and also features that are present here. That is why you can see finally we ended up having 31 unique features among the two samples. Yeah, it's better to let go some features to increase the samples when you want to do experiment. It's very good to mention this. So you have to give priority to the size. Yeah, we want the quality of the data, but at the same time, in machine learning, size is very important. So because the what we used to refer to as the hypothesis function principle says that if it works on enough data set, it will work on unseen data set. So what data is enough is a relative term, but usually the more we are, the better. So sometimes you want to, for example, we want to keep just 45 features. So we use only 196. We don't want to merge because these are unique to this, 39 are unique to this. But rather it's better to look for what are unique among the two, and then you come up with more samples. Of course, we reduce number of features. Even in reality, 31 feature is still more. Still more. You can say too much. Imagine someone wants to use some medical application and they have to do clinical tests of up to 31 tests. That is too much. So we want to reduce it as much as possible. So to see that, okay, can we get the same accurate result while using fewer medical tests? So in the experimental setup, of course, so you can see here the data source, two data sets combined together. Under the pre-processing, we have the label encoding techniques, the query technique, and some missing value imputation using the mean. Sometimes you have missing value. If the missing values are not too much, then we go for treatment of those missing values. The best way to treat missing value, and we discussed this in our earlier videos on pre-processing methods, is to go back to the original source of your data set and try to get the correct result from them. But often than not, sometimes, most cases, it's not possible. Maybe the source of the data is no more existing, by the way. Even if it is existing, they have forgotten where the mistake actually came up. So that is why we go for, here we make use of mean. That is to find the average of that particular column and use it to replace the missing values from there. So we have median and so many other methods of treatment. So if there is time, somebody might want to investigate the effect of missing value treatment on the performance of a data set. This is another research topic somebody wants to go about. We want to see how does the choice of missing data treatment method you have selected affect the performance of the model. In that case, you have to use the available options, like the k-means estimation, mean, median, the commonness among the attributes, and host of other methods that we can use. And then try to compare them together, which one gives you a better result. However, when you are dealing with a big project, sometimes you just have to go with one that you think maybe big based on your experience, okay, this should work. And then it worked, and finally we're able to have like maybe 94% accuracy. For the beginning, this is okay, but there's still big room for improvement for further research output. So here, the percentage split is taken 70% for training and 30% for testing. I said this is very important using the stratified ratio. Stratified ratio means these splits are done in such a way that the number of samples from each classes are evenly distributed. So you don't want majority to be in the training while minority will be in the testing for one particular class. So this is what we call stratified sampling. So then move on to the experiments. And then you try to say, okay, this is experiment one. Experiment one without smooth. Smooth is used to do balancing. If the data is imbalanced, we use smooth to balance the data. It's one of the means of balancing, of correcting data imbalance problem. So experiment two is with smooth. So this one is original data set with imbalanced data. So because one of the samples is more than the other sample. But here, without and with it. So then we have the experiment. Grid search was used to check. Grid search with 10-fold cross-validation was used to search for the hyperparameter. This is for hyperparameter optimization. Then finally, the experiment one, that is, so it was decided to go ahead with two sets of experiments separately, the one with balanced data and the one without the balanced data. So later when we go into the detailed paper, maybe in our next episode, we're going to see the details of how these experiments were carried out and which of these two actually show maybe better improvement among the others. Now, so in the experiment, we can see that the combination of 3 support vector machine, as the case may be, and also the support vector machine logistic regression and the 2 other boosts were combined appropriately in getting the best result possible. Also, feature selection using sequential forward feature selection and sequential backward feature selection were explored. And then, of course, the evaluation of the model, accuracy, precision, recall, and then the ROC, among others, were utilized. And the upper parameter tuning, so which is very, very important, we say that we need to invest more time on it. Without upper parameter tuning, you might not be fair to the model. So this was carefully carried out, in which case, these are some of the parameters were searched in range for SVM and also of other and the other machine learning algorithms. See, the hyperparameter, the simple method, the grid search, no one really guaranteed that you're going to have the best value possible, but you need to make sure you carry out a particular hyperparameter tuning system so as to be sure that you are fair to the model. But however, there are so many methods of hyperparameter. The simple one, just checking one by one after the other. The grid search, the problem with grid search is can take a lot of time, and you have to do two at a time. See? And then using genetic algorithm and also several other nature-inspired optimization algorithms that have been developed that could be employed to actually look for the best hyperparameter for the system. But the good news is once you select any one that is simpler, I always say in machine learning, keep it simple. It is when the simple method doesn't work that you can start worrying about going to more complicated one. Because there's nothing that guarantees that the complicated method will work for you. So that is why go for simple one. If it failed, then you go for another more, maybe sophisticated one until you get it. Because let the data speak is always it should be our guiding word here. Let the data speak. Let the data speak. Sometimes using very complicated method might miss the data, might miss the performance because of the distribution of the data. So that's why machine learning always say, keep it simple. Start from simple methods, and then gradually you can increase the complexity of your algorithm or the hyperparameter search method. So the hyperparameter search they were searched within some range for each of them to make sure that each of them have been subjected to appropriate hyperparameter. And these are some of the hyperparameter tuning to the optimal values, which I said are very, very important when you run experiment. You need to provide the optimal parameter value so that other people can be able to replicate your result. This is very important, as the case may be. You can see these are the individuals. These are the individuals. So, and finally, implementation of the voting ensemble then was carried out. That is, you can see here, 3 SVM were developed. See, the idea of ensemble, you see 3 SVM were developed, SVM1, SVM2, SVM3. 2 of these were developed, and then 2 of these for this. Based on the performance of the model, we'll try to see, okay, which one gave us the best result for them. Why for this one also 3, and then 1. And then finally, you find the voting. This one will give result. Then you get the voting classifier that when the test result comes in, the test samples comes in, then it will determine what is the final classification result. So these are all both implemented for the data that's not balanced and for the balanced data. Now, also this feature selection, the sequential forward and backward feature selection was carried out. And then it started by using all the features to build the classifier in the first step and then build several classifiers iteratively, eliminating one attribute at a time until an optimal feature subset is obtained. So this is a form of a kind of trying to exhaustively look for the combination of features that can work on a particular problem. So then these are some of the results of the outcome of the feature selection. So each of them was subjected to it. We can see here that for the experiment 1, this got the best result. So for the experiment 2, see, this is what came out here. With this one, is still try to outperform. However, it's to be we need to take note that the experiment 1, which of it happens to be the imbalanced data, actually got the best result, as the case may be. This is again what we used to tell people, that when you have your data, run the experiment on the natural data, on the original data, before you start balancing or not balancing. Run the original experiment. Let's see what the data is saying. Because I've seen cases where the data that is not balanced actually outperformed the one that was finally balanced. See? So this is in line with the principle of let the data speak. It is when we are not able to get better result with unbalanced data, then we move ahead to investigate the balanced one and see that, okay, maybe we're going to get better results. So in summary, the proposed final ensemble model was the one that actually showed the best possible performance, which is 94% accuracy. So the proposed voting ensemble techniques could accurately diagnose rheumatoid arthritis with an accuracy of 94, a recall of 96. So with 30 clinical features when utilizing original data sets and sequential feature selection. Even though sequential feature selection were carried out, but however, this method achieved better result with 30 clinical features. Personally, to me, it means a huge work needs to be done, because having to diagnose with 30 features is a lot of numbers. We need to bring them down. So we need to bring them down drastically to as low as possible. But the good news, at least at this level, achieving 94% accuracy, you can see here, this is the confusion matrix. You can remember here, this is the one we call false negative. That is false negative, while this is false positive. You say it's getting lesser of the bad mistake. This is a mistake, this is a mistake. But false positive is a lesser evil when it comes to error in classification. So this is the most serious error. So it's getting lesser number of that serious error compared to, so that's why it's a little bit a good achievement. And also upon that, and here you see also the area on that curve. You can see here, we say we are looking for perfect one, which is going to be like this. It's not perfect, but it's close to that particular place. So we want to believe there's a lot of opportunity for people to really come in here and then to say, okay, how can we bring down, especially how can we bring down this number of issues? 30 is much. It's enormous, by the way. So we need to try to bring it down. So that is why this is just a brief summary. So we're going to, in the next edition, we're going to look into the full paper itself, what has been carried out inside it in detail, one after the other, as we usually do, so that we can see how to do that or how to replicate such in your own area of application. Future work include trying to include more data sets from other repositories, to explore clinical laboratory tests that are more correlated with the target class, investigate other feature selection techniques to reduce the number of features required to attain reliable outcomes. So we want to check from other feature selection techniques because to me, 30 is still very high. We need to bring it down. So to as low as maybe 5 or 6 or 7 or thereabout. Also extend the proposed voting ensemble to incorporate more classifiers. So one of the established principle of ensemble is the more the number of classifier you are combining, the higher the possibility of getting better result. So here we just have 3 plus 2 plus 2, I think maybe 7. So can we increase it to like maybe having like 101 classifier and let 101 classifier meet together and vote to determine the final prediction? Hopefully this will take the result to a very high level, depending on the case. However, that's not just rule out. Even simple classifier can still be explored, especially when it comes to feature selection. Because presently we're having 30 features upon 446 samples. So this is a very lot of cost of dimensionality problem. I mean, with 30 features, you are expecting 10 raised to power 30 samples. Just do the mathematics. So how many samples we are supposed to have? But this is the only thing we can get. So for sure, we still need to bring down, especially the feature selection, need to do a lot of work to push it forward. But as it is, the system has been able to achieve, at least with the total number of data set we have, like 446, that is making mistake of just 8 samples, and 5 of them are coming from less critical mistakes. False positive means you are predicting that somebody is having rheumatoid, meanwhile he doesn't have it. You have to go for follow-up and then they will claim that you are fine. But here is a critical mistake that we don't want false negative, saying that someone is not having the disease, and then he will go about until it develops into complicated chronic disease, which we don't want. So, but 8 mistakes out of 446 or thereabout, I think is still something that is excellent for a start. So, but definitely there are a lot of work that needs to be done to push it to another level. So this is just a short summary of what we're going to be discussing. Maybe hopefully in the next one we consider about to see the details of how this experiment have been carried out, and also for that thing, and see how we can also use it to motivate us to do our own individual work in our own various areas of application. So thank you all. So if there is question, we're going to take a couple of questions before we call it a day. Thank you.